In this video, we're going to wrap up a tiny little sliver of section 19.4, and then we'll be able to launch into talking about Gibbs free energy. So let's start by discussing entropy changes in the surroundings. We already know how to calculate the entropy change of a system, but we want to be able to calculate entropy changes in the surroundings. Well, we'll find that heat that flows into or out of the system will change the entropy of our surroundings, because we know if temperature increases, we increase entropy. If temperature decreases, we decrease entropy. So if heat flows from our system into our surroundings, it will increase the entropy of the surroundings. For an isothermal process, we can say that this is true, that delta S of our surroundings is equal to negative Q of our system minus the temperature in Kelvin. Delta divided by the temperature in Kelvin. So negative Q of our system divided by the temperature in Kelvin. If a reaction happens to be at constant pressure, then Q of our system is simply going to be equal to delta H for the system. And again, this is true. The Q of our reaction is equal to delta H of our reaction at constant pressure. So we'll get this. So delta S of our surroundings is equal to this. That means that we can fill in all of the components of our second law of thermodynamics, which tells us entropy change of the universe is equal to entropy change of our system plus entropy change in our surroundings. And since we know that the entropy change of the universe is greater than zero, if we add those two things together, it will tell us whether that process is spontaneous or not. So let me show you what I mean by that. So our second law tells us this, that the entropy change of the universe for any irreversible or spontaneous process is going to be greater than zero. The entropy change of the universe would be zero for a reversible process, but as you may remember, reversible processes are a little bit boring. Nothing really gets done with a reversible process. When it comes to when is delta S of the universe going to be negative, the answer to that is never. Never. You would need a time machine for delta S to be negative. So we will never find the delta S of the universe to be negative. So we know that the universe comprises two parts. There are only two parts to the universe, the system and the surroundings. So we can write that the entropy change of our universe is equal to the entropy change of our system plus the entropy change of our surroundings. Well, we already know how to calculate the entropy change in our system. We just use the standard molar entropies for our reactions. Calculating delta S of our surroundings, we just did that with the delta H and the temperature. And so we're going to do this for an example. So we can determine if a process is spontaneous by calculating delta S of the universe and seeing if it's positive. If it's positive, then yeah, the process is spontaneous. Doesn't mean it'll happen, but it will tell us if it is spontaneous. So let's do that. So let's look at delta S of the universe for the Haber process. Previously, I showed you that delta S, Previously, I showed you the Haber process, and here is the Haber process. Delta H and delta S have these values. The gases are at 1 atmosphere and the temperature is at 298. We want to calculate, we already have delta S of our system right here. We want to calculate delta S of our surroundings, and we're going to get that from this. So if delta S of our surroundings is equal to negative delta H of our system divided by the temperature in Kelvin, then we'll just take that value that is delta H of our system, which is the negative 92.38 kilojoules. We'll have negative of a negative, which will make it positive. We'll divide by 298, and we get 0.310 kilojoules per Kelvin. Typically, typically we will find that entropy values are given in joules per Kelvin, not in kilojoules per Kelvin. It's just a convention that we like to use. So we can calculate delta S of the universe now. We have delta S of our system. We've got delta S of our surroundings. We'll throw those two numbers together in this equation. So delta S of system plus delta S of surroundings. So there's the negative 198.3, the positive 310 joules per Kelvin, and we get positive 112 joules per Kelvin. Well, because that is a positive value, this reaction should be spontaneous at standard conditions. Now, I'm going to warn you about something. Just because it's spontaneous at standard conditions doesn't mean that it actually happens. The fact of the matter is, if you take nitrogen and hydrogen and ammonia, that it will not reach equilibrium regardless of what you do. It will not reach equilibrium at 298 Kelvin. The activation energy is just way too large. If you go back to chapter 14 and look where we talked about activation energy, the larger the activation energy, the slower the reaction. Well, this reaction is so slow at room temperature that it essentially never happens. You could wait thousands of years and never ever get any appreciable increase in the concentration of your ammonia. But that said, we can calculate it at 298, but just be warned, even though the delta S came out as positive, it doesn't tell us whether we can actually do it or not. So that's our big caution about thermodynamics, is that it is separate from kinetics. Okay, so now that I've shown you that, what does that mean? Positive 112 joules per Kelvin. Well, it's positive, so we know that that means that this should be a spontaneous process, but that number by itself doesn't mean a whole lot to us. A joule per Kelvin, an energy per unit of temperature, that doesn't mean a whole lot because it's hard to think in entropy. Our brains can think in energy okay, but thinking in entropy is a little bit weird. So we're going to introduce a new topic, or a new concept that's called the Gibbs free energy. So the Gibbs free energy. Calculating the entropy change is interesting and it is a little bit useful, but that number isn't useful in and of itself. We can't do anything with that positive 112 joules per Kelvin by itself. So we can take that equation that we just used to calculate delta S of the universe and manipulate it. We love manipulating equations, so we're going to manipulate this. We're going to multiply both sides of this equation by negative t. When we do that, we're going to get negative t delta S of the universe is equal to delta H of our system minus t delta S of our system. What's great about this is that we've got the universe defined in terms of our system, and we'll find that this negative T delta S is now an energy term, not an entropy term. And that will make all the difference. It turns out that negative T delta S of the universe is the Gibbs free energy. So it tells us whether the process is spontaneous. Now we know if delta S of the universe is positive, then the process is spontaneous. Well, if delta S of the universe is positive, then that means this quantity, negative T delta S, is going to be negative. That means if the Gibbs free energy is negative, the process is spontaneous. If the Gibbs free energy is positive, the reaction is not spontaneous in the forward direction. Now, we want to be able to relate delta G to our equilibrium position. So we are going to use that equation here in just a few minutes, but we want to relate delta G to our equilibrium position. And we can do that by looking at a few definition values. So if delta G is less than 0, we just talked about this, that means that the reaction or process is going to be spontaneous in the forward direction. Going back to chapter 15 where we compared Q to K, that's the situation where Q is less than K. So when delta G is less than 0, Q is less than K. That's a good thing to remember. If delta G is equal to 0, that's the situation where our process is at equilibrium. If delta G is equal to 0, then Q is equal to K. And then finally, what about if delta G is greater than 0? Well, you can imagine that means the reverse reaction would be spontaneous and Q would be greater than K. Okay? So if you're having trouble remembering that, go back and look at chapter 15 on the section comparing Q to K. That would be a useful thing to look at. So now we've got the Q and K. We're going to talk about the Haber process again. So here's the Haber process, and I'm going to show you a new kind of diagram that I haven't shown you. And this is it's a free energy diagram. It's a little bit unusual, so we'll unpack this. It'll just take a few minutes. On our x-axis, we don't have a traditional x-axis that has any range of values. On our x-axis, we've got this point, which is 100% of our reactant. So we have 100% in the form of hydrogen and nitrogen. All the way over on the right on the x-axis, we have 100% products. So this is where we only have ammonia. We don't have any of our reactants. Well, we will find that the equilibrium rarely, by rarely, never, is going to be 100% reactants or 100% products. Now, I suppose if you wrote down a crazy equilibrium, yes, you could have it as 100%. But in any case, we will find that there is a point in between where the equilibrium position is. On the y-axis, we have the free energy. And imagine that your process is a ball that we put onto this surface. Well, that ball is going to go to the lowest point. And so we will find that the equilibrium will go to this lowest point. If it's over here, it will proceed to the right to go down in free energy and be spontaneous. And if it's over here, it will go to the left to go down in free energy. But in either of these cases, we will find that here it was not at equilibrium, and down here it will be at equilibrium. So that is a free energy diagram. It's just another way of thinking about how these things relate. So Gibbs free energy of formation. Okay, we talked about enthalpies of formation back in chapter 5. And the enthalpy of formation was the enthalpy for a reaction to form a substance, 1 mole of a substance from the elements in their elemental form. The Gibbs free energy of formation is essentially the same definition. It is the Gibbs free energy for the reaction where 1 mole of a substance is formed from its constituent elements in their elemental form. And just to show you a couple of examples of these, I've got here ammonia. So on the left, we've got half a mole of nitrogen plus 1.5 moles of hydrogen, and that is in equilibrium with 1 mole of ammonia. Our delta G of formation here is negative 16.66. That means that if we put this particular substance, if we put these particular chemicals, one atmosphere of nitrogen, 1 atmosphere of hydrogen, and 1 atmosphere of ammonia, that this reaction would have a negative delta G, and that the reaction would proceed in the forward direction. So we would create more ammonia, and the partial pressures of nitrogen and hydrogen would decrease. All right, there's a couple of requirements for these kinds of equations, and they're just like the requirements for delta H. The first requirement is that the things on the left have to be their elements in their elemental form, and the things on the right have to have a coefficient of 1. Of course, these have to be balanced equations as well. And then these delta G of formation values, we can find them in appendix C, just like where we found the delta H of formation values and where we found the standard molar entropies. So here, this one is for water liquid, and you'll see it's negative 237.13 kilojoules per mole. That is the enthalpy of formation, or the Gibbs free energy of formation, not enthalpy. Enthalpy is a different number. And then look what happens when instead of H2O water, we choose H2O gas. Well, we get a delta G of formation that's negative 228.57. So it is a different number. Now, it's not hugely different, but it is a different number. And the reason it is a different number is because these are in different states. The states matter when it comes to these Gibbs free energies. On this one, I wanted to pick one that had a positive value for delta G of formation, just so you understood that it's possible to have a positive value for delta G of formation. If we took 6 moles of carbon graphite and 3 moles of hydrogen gas and created 1 mole of benzene, that reaction would have a delta G of formation of positive 124.5 kilojoules per mole. Well, with that value, this reaction is not going to proceed in the forward direction. This is just not a spontaneous process at standard conditions. To get this reaction to happen, you would probably have to increase the pressure of that hydrogen pretty substantially to push it to the right. And even then, this is going to be a challenging reaction to do. That said, there are better ways to make benzene. I will just say that. One, you can just distill it out of crude oil. There's plenty of it in there. All right. And then here, I know this last reaction does work. I have seen this one in person happen before. It's pretty cool. If we take 1 mole of sodium, half a mole of chlorine, and produce 1 mole of sodium chloride, that will have a delta G formation equal to negative 384. That one definitely is going to be spontaneous. This one will happen all by itself. The ones with water, we could do those. The first one, even though delta G is negative, that one, the activation energy is too high at 25. And then this one is pretty much impossible to do as stated. But we will find these numbers are useful in order we can use these to calculate other things. Now, I want to point out that all of this data is stuff that I got from Appendix C, and I'm going to tab over to Appendix C so you guys can see what that looks like. So here is Appendix C. One of the ones we just had there was ammonia gas, and it had right there, ammonia gas had a Gibbs free energy of formation of negative 16.66 kilojoules per mole. All right. One thing I do want to point out is a lot like with the enthalpy of formation, the Gibbs free energy, here I'm going to scroll down, the Gibbs free energy is this middle column. The Gibbs free energy for an element in its elemental form will also be 0. And that's because the definition is what's the enthalpy to form, or what is the energy to form it from its elements in its elemental form. If it's already in its elemental form, it's going to be 0. So there we go. So pretty interesting there. We're going to be using this table quite a bit. Both all 3 of these quantities now. We're going to use delta H of formation, the Gibbs free energy of formation, and the standard molar entropies. So exciting. All right. If we've got a reaction that is at standard conditions, and what that means is it has to be at 25 degrees Celsius or 298 Kelvin. All of the gases, if there's any gases, need to be at 1 atmosphere, and all of the substances in solution are at 1 molar. Well, if we know those quantities, then we can calculate the change in Gibbs free energy using the Gibbs free energies of formation. Okay, and our formula for doing this is this. This is just like the one that we saw for entropies a little while ago, and it's also very much like the one we saw for enthalpies back in chapter 5. And then here the quantities N and M are the coefficients in the balanced chemical equation. So that is how we calculate that. Now, I'm going to show you how to use this, and then we're going to do an in-class assignment problem. So let's do the combustion of methane. We'll determine the delta G value for the combustion of methane at 25 degrees Celsius. So there's methane plus oxygen gives us carbon dioxide and water. And you'll notice the water here is in the liquid phase. If we put it in gas phase, we would get a slightly different number. So here are the Gibbs free energies of formations for each of these. So so these are the numbers. I'm not going to read those out right now, but to do the calculation, we'll want to do the coefficients times each of these values. We'll do products minus reactants. So here is a sample calculation. So we'll do 1 mole of the carbon dioxide times negative 394.4. That's this calculation. 2 moles of water times negative 237.13 kilojoules per mole. And then for the reactants, we've got 1 mole of methane times negative 50.8 kilojoules per mole. And then I went ahead and put in 2 times 0, even though you don't technically have to write that out. I went ahead and put that in because that way I can keep track of that. I can come back and recognize why I did that a little bit later. So if we put these quantities together, here we're going to have minus a negative. That means just be careful when you're punching these kinds of things into your calculator, because this happens all the time. Not every time, but many times. So just be aware of your signs. And then here we will get -1 or -817.86. Because of significant figures here, this goes to the 10th place, the 100th place, the 10th place. We're going to round this to the 10th place, and it becomes -817.9 kilojoules. Well, that's negative, and that negative value tells us that this reaction is spontaneous in the forward direction. And how? It is quite spontaneous in the forward direction. So we're going to hold on to that number because that number is going to be quite useful after I show you this next calculation. So you might want to write that down, get a tattoo of it, whatever it takes to remember that number. You won't have to remember it for the test, so no tattoo necessary, but you get the idea. If you want to calculate delta G at any temperature, let's say you don't want to be restricted to 25 degrees Celsius, and I can hardly blame you. I mean, 25 degrees Celsius is a pleasant day, but it also means there's a limit to what kinds of reactions we can do. So if you want to calculate delta G at any temperature, then you can use our delta G, our delta H of the reaction, and the delta S of our reaction in this formula. Delta G standard is equal to delta H standard minus T delta S standard. This will work at any temperature, including 298, but it will work at temperatures other than 298 as well. So it will work at any temperature, including 298 or 25 degrees Celsius. Now, one quick note about this particular calculation. Using this at temperatures other than 25 degrees Celsius makes the assumption that delta H and delta S of the reaction don't change as we change the temperature. That is an approximation that's not quite true. It just so happens delta H and delta S do change a little bit as the temperature changes, but we're going to treat them as if they're constant across all temperatures. But just be aware, the further we get away from 25 degrees Celsius, the more uncertainty and the more that approximation may start to break down. That said, we're not going to let that discourage us from doing a useful calculation. So we're going to take that same reaction that's the combustion of methane that I showed you a few minutes ago, and we're going to calculate delta H and delta S first. Here are the enthalpies of formation and the standard molar entropies for each of these substances. These all come from appendix C. So I looked all of these up in appendix C when I did this calculation. And let's do the delta H calculation first, products minus reactants. Now I'm not going to go through all the details, but just remember we're taking the coefficients and multiplying by each of these numbers for the products, and then we're going to take the coefficients and multiply each of them by the numbers for the reactants, subtract the reactants from the products, and we will get this. So here our delta H for this reaction is negative 890.4. Again, I rounded to the tenths place because of sig figs. So negative 890.4 kilojoules. That number, because it's negative, tells us that this is exothermic. It's also a very large negative exothermic quantity, which means it gives off a lot of heat. That's not surprising. When you burn methane, it will give off quite a bit of heat. For calculating entropy, before we calculate entropy, let's take a guess. So we look at how many moles of gas we have on the left. So 1 plus 2, so 3 moles of gas on the left, and we only have 1 mole of gas on the right. Well, since it's going from 3 moles down to 1 mole, we would predict that this would have a negative value for delta S, and we would be right. So here we go. Delta S, again, products minus reactants. I'm not going to go through the details of the calculation other than to say I did double check these. And then there is the difference, and you'll see that we do indeed get a negative value for delta S, negative 242.9 joules per Kelvin. So that is our quantity for the delta S. We now want to take that number and the enthalpy and put them into the delta G equals delta H minus T delta S. So again, we're taking these two values, our delta H and our delta S, and we're going to calculate delta G. So here is our equation for delta G. We calculated delta H and delta S. Our temperature was 298. So here's our delta H, negative 890.4. Here is our temperature, so minus T. There's our delta S. That negative value for delta S. And there's one last little bit that we need to do to get it so that these are the same units. We need to multiply by 1 kilojoule over 1,000 joules, and that will cancel out our joules and give us kilojoules. So these will be in the same units. And you'll see that gives us a delta G equal to negative 818.0 kilojoules. If we compare that to our previous value that we did when we used the delta G of formation, we got negative 817.9. Very close. That, I'm not even going to call it rounding error. I'm just going to call it a rounding difference. So that is just a rounding difference. Okay, well, after talking for a very long time here, we now need to do some calculations on number 51 and 53 on the in-class assignment. So I'm going to switch over and do that. So here on number 51, for a certain chemical reaction, delta H is negative 35.4 kilojoules. Well, right away, that tells us, is this reaction endothermic or exothermic? And that means it is exothermic because delta H is negative. So I'm going to say exothermic, and that's because delta H is less than 0. And I'll put delta H standard is less than 0. We now want to calculate delta G for this reaction at 298. Well, delta G is equal to delta H minus T delta S. Now I'm going to come over here so I have a little bit of space to do this. So delta G is delta H, or delta H is negative 35.4 kilojoules minus T. Our temperature here is 298, so 298 Kelvin. Our delta S is negative 85.5 joules per Kelvin. And just like we did on that PowerPoint thing, we need to convert these joules into kilojoules so that we'll have the same unit. And so that is going to be 1 kilojoule over 1,000 joules. So now I'm going to turn my camera just a bit here to get that calculator clearly in view. And so now we're going to do this calculation. So negative 35.4 minus, and we're just going to multiply all these out, 298 times negative 85.5 divided by 1,000. And because order of operation, we'll do all those before we do the subtraction part there. And we're going to get negative 9.921. So delta G is equal to negative 9.921 kilojoules. As far as sig figs, this is in the 10th place, so the furthest we can go is the 10th place. So we're going to go ahead and round that. We're going to round that to negative 9.9 kilojoules. Well, that tells us that this reaction is spontaneous in the forward direction. So this reaction is spontaneous in the forward direction. Okay. So we now want to look at number 53. So we'll flip over to the next page to get to number 53. And 53 is actually two problems. So 53 is two problems. And so here, both of these are fairly involved problems. In order to do this, we want to calculate delta H, delta S, and delta G at 298 for both of these. We're going to have to dig these numbers out of Appendix C. And then once we calculate delta G using delta G of formation, we're also going to calculate delta G using delta H minus T delta S. So we've got quite a few calculations to do here. So I'm going to put these. So delta H of formation. I'm put the delta H of formations first. Put the delta G of formations next in the standard molar entropies. And the reason that I'm writing it in that order is that in the appendix, that is the order that it is written in. Okay, so we're going to look up hydrogen, fluorine, and HF. They will all be right there next to each other. So the hydrogen, the fluorine, and the HF. So they'll all be right there next to each other. And before we look, there are a couple of these that we know before actually looking at the table. And the ones that we know are the elements in their elemental form. So hydrogen, H2 gas, that is the elemental form of hydrogen. Fluorine, F2 gas, that's also the elemental form. So we'll find that the delta H of formation for both of those and the delta G of formation for both of those are going to be 0. However, all the other 5 numbers that we have here in this little mini table, we're going to have to look those up. So let's go over to Appendix C, and here is the hydrogen and fluorine and the HF. They're all kind of crammed in there together. So let's do hydrogen first. So hydrogen 0, 0. And our entropy is 130.58. And so our next column is fluorine. So there's fluorine 0, 0, and 202.7. And then for HF, we've got 3 terms here, negative 268.61 kilojoules per mole. That's our enthalpy. Our Gibbs free energy, negative 270.70, also in kilojoules per mole. And then finally, for our entropy, 173.51. So 173.51 joules per mole Kelvin. Once we have those quantities, and I've written them down, I'm now going to flip back over. So I'm now going to flip back over and we can do our calculation. So we'll start by sort of separating that out, and we'll start by doing our calculation for delta H. So products minus reactants, we've got 2 times negative 268, so 2 negative 268.61 minus 1 times 0 plus 1 times 0. All right, and when we do that calculation, so 2 times negative 268.61, and that gives us negative 537.22 kilojoules. Okay, so let's do the delta G. So delta G, again, products minus reactants. All right, so there are our products, there's our reactants, and this one is an easy calculation here. So we'll do 2 times negative 270.70, and we get negative 541.4, and we could put 40 there, so negative 541.40 kilojoules. So the delta H tells us that this reaction is exothermic. The delta G tells us that this reaction should be spontaneous in the forward direction at 298. Now let's calculate the entropy change. Because this has 2 moles of gas on the left and 2 moles of gas on the right, we will find that the entropy change is going to be quite small. There is a little bit of an entropy benefit because here we've got symmetrical molecules and here we've got an unsymmetrical molecule. So going to an unsymmetrical molecule will increase the number of microstates ever so slightly. However, it's not a very big change. So let's calculate that delta S. So again, products minus reactants. So 2. And let me check that number. That's 202.7. I just want to make sure I had the right number there. 202.7. And now we just need to calculate that. So 2. All right, I put that in parentheses, and I didn't put the one, I didn't actually type the ones in because that's implied. Just making sure I put the right numbers in. And the number we get here is 13.74. Let's see, hundredths place, tenths place. We're going to round that to 13.7. So approximately 13.7 joules per Kelvin. That is a very small change in the entropy. And again, the reason it's such a small change is that we've got 2 moles of gas on the left and 2 moles of gas on the right. So that's going to give us that very small change. So now we want to do an additional calculation here. And our additional calculation is we're going to do delta G is equal to delta H minus T delta S. Just because we want to prove that if we take these two values and calculate the delta H and the delta S and calculate the delta G, we should get the same number, or at least within rounding error difference. So our delta H is equal to negative 537.22. And that is, let's see, so it's minus T delta S. So I'm going to go ahead and write the kilojoules out. So negative 537.22 kilojoules minus 298 Kelvin. And then our entropy was 13.7 joules per Kelvin. And then 1 kilojoule per 1,000 joules. And that will give us the correct units over there. So that will give us our answer in kilojoules. All right, I'm going to clear all that, and we'll put negative 537, and I've got to put this here so you guys can see it. So negative 537.22 minus, and since we're multiplying all these, I don't need parentheses, 298 times 13.7 times, or not times, divided by 1,000. And that gives us negative 541.3 kilojoules. And if we compare that, if we go back up here and compare that, the delta G value we got when we used delta G of formation was negative 541.4, and here we got negative 541.3. And I think everybody would agree that that is, those are very, very close to each other. So those are very, very close to each other. Okay, so let's do this last one, and I'm going to do a little bit of magic, which is I'm going to pause the video just for a second and write down the quantities for the delta H of formation, the delta G of formation, and the standard molar entropy, so that you guys don't have to sit here and watch me just write down numbers from a table. You guys can look these up on appendix C. And magic, there we go. I have written them down. Again, I think having you watch me write those out is a little bit tedious, so we can avoid that tedium. So now let's calculate delta H, delta G, and delta S. Delta H, again, products minus reactants. I suppose this is tedious as well, but maybe you can fast forward through this part. Okay, so coefficients times each of those numbers in the delta H, and when we punch those numbers into the calculator, we will get the correct answer. So I'm going to do 84. We're going to do negative 84. So negative 84.68 plus 2 times negative 241.82, and that is this part. So that is this part. And so now we're going to subtract this. So we need to put this in parentheses. 2 times negative 201.2 plus 0. Well, I guess I didn't need to put that in parentheses if we have a 0 there. And that is going to give us a total of negative 165.92. And I'm going to look. So negative 165.92. And because of, because of significant figures here, hundredths place, tenths place. Hundredths place, yeah, so hundredths place, tenths place. We're going to round that to the tenths place. So we're going to put negative 165.9 kilojoules. All right, so that tells us that this reaction is exothermic. For delta G, so again, products minus reactants. I'm just going to shut up for a minute. In fact, I'm going to turn my microphone off for a sec. All right, so here we calculated negative 166.2 kilojoules as the Gibbs free energy. You'll often see for a lot of reactions that the change in enthalpy and the change in Gibbs free energy are comparable. They're not the same, but they are comparable. So they are often relatively close to each other. So now let's calculate delta S. Again, I'm going to turn off my mic. Okay, well hopefully everybody can see what I did. Sorry the numbers got cramped over here. I'm going to circle or put in red around the important ones, the rounded values. So that top one is the delta H, this is the delta G, and here this is the delta S. You'll see that that delta S is a very tiny number. 1.4 is a ridiculously small number. And the reason it is so small is because if we look, we've got 2 moles, 2 plus 1, that's 3 moles of gas on the left side, and 1 plus 2, that's 3 moles of gas on the right side of the equation. And that definitely is a very small, that's going to give us a very small value for delta S. Okay, that all said, we do have our value for delta G, which was the negative 166.2. That reaction is spontaneous. But now, here, I'm going to do this in a slightly different color. Now we're going to calculate delta G is equal to delta H minus T delta S. So for our delta H value, we had negative 165.9 kilojoules minus 298 Kelvin for our temperature. Our entropy was 1.4 joules per Kelvin, and then 1 kilojoule over 1,000 joules. And you'll see that this delta G and delta H are almost the same value here because of such a small value for delta S, but we'll do the calculation anyway. So I'm going to clear all that. We'll do, make sure you can see my calculator. You can. So negative 165.9 minus 298 times 1.4 divided by 1,000. And here we get 166.3. So negative 166.3 kilojoules. And you'll see that if we compare that to the delta G that we got using delta G of formations, that it's almost the same number. It is just a rounding difference. Okay, wow, that was a long problem. So definitely a long problem. Before we go on to how does delta G change with temperature, that is an important concept. So I'm going to put that onto the next video, and we will see how that works here in just a second. So